Okay, so thank you everybody for attending my talk that I've tried to make as boring as possible despite the title. That's what it is. So what we're gonna see today is continuous optimization algorithm, and what we're gonna try to do with that is to see if we can run it with multi-precision. So what we're gonna try to do is to try to save as much computational cost as possible when running this algorithm. So a bit blurry right now, but I'll give you more context in the talk. So this is the plan of the talk. First, we're going to see basics of continuous optimization and one particular algorithm to solve continuous optimization problem, which is a gradient descent. Then I'm going to give you some context about multi-precision computations. And then we're going to move to the particular context that we're interested in this topic of finite precision computation. So basically, any computation that's run on your laptop. And how we can include that with our gradient descent algorithm, which is called R2 in our case. So how can we adapt this gradient algorithm with this multi-precision relative to finite precision in your laptop, this algorithm? Okay, so basics of continuous optimization that you're probably most familiar with in this room. So we have a continuous smooth function. We're going to consider it smooth in this one, which is our optimization function. So f, and we're going to try to find the minimum of this function, which is here. Okay. So f is a scale value function in that game Rn to R. So n here is dimension of the problems, and E is going to be our optimization variables. So how can we find this global minimum here on the problem here? Okay, well, doesn't matter. So we're going to start from an initial point here, and we want to find this guy there. So how can we find this minimum? So the idea is to simply, with the gradient descent algorithm, go down the slope. Okay, so here I look at my slope at x, and I said, okay, I'm just gonna go on the right-hand side because this is where my function decreases. So what does it mean? It means that I'm gonna build the first order Taylor model, okay, which is my slope. My slope here in red is the first order Taylor model, basically, of my objective function. And here the Taylor model, what we have, the Taylor model, we're going to call it local model because it approximates locally the objective function. And this model here is built from the objective function and its gradient here. Nabla f is the gradient. So if I want to go down the slope, I'm going to make a step on the right-hand side. Basically, I'm going to go in the opposite direction of the gradient. Okay. Here at x, my gradient is negative. So if I want to go on the right-hand side, I'm going to have to go to the direction, opposite direction of the gradient. And I'm going to multiply that by alpha, which is a step size parameters that enables me to choose if the step is big or small. Okay. And after what I'm going to do is I say my next turn point is x plus the step I just made. I'm going to repeat, build the local model, go down the slope in the opposite direction of the gradient. So, yep. I'm gonna make a step, new current increment, and I'm gonna go again to step 1 and so forth until I converge not to the global optimum I wanted, which is here, but to local optimum. Okay. And the local optimum I'm going to converge to depends on the initial point I've chosen. So if I want to find another better point, better minimum, I'm going to have to solve the algorithm again from another initial points. So that gradient descent algorithm, pretty basic, that is guaranteed to converge to local minimum. So how can we improve the gradient descent algorithm? So one thing we can do, and that can happen, is that maybe my step is too big. That is, the objective function at my incumbent plus the step s is actually higher than the objective function at my turn points. Okay, so basically I do not decrease the objective function. If I make this step, I'm going to increase the objective function. So what we're going to try to do is to evaluate the objective at the new candidate. So that's we're going to call the candidate, makes this test, and check if it actually brings a decrease in the objective function I try to minimize. And if it does not, I'm going to not make the step. So what I'm going to have to do is to find, to make it a smaller step. Okay, so basically, if my step is too big, what it tells me is that my local model, so the slope, the red slope, my Taylor series function, is good locally, but not that good if I make a step too big. So what I want to do is to decrease the step size. And how do I know if my model is good or not at my candidate here? So one way to have that is to compare the objective decrease, which is the numerator of this ratio rho here, with the model decrease. That is the decrease I expect of the objective with my model. And if this ratio is not good, so for example, here, delta F is negative, with an increase of the function, and here, delta T is actually positive. So there is a difference in sign. So rho is negative, telling me that the function increases here, and that's not good. So if this indicator rho tells me that my model is not good, what I'm going to do is I'm going to decrease the step size parameter alpha to make a smaller step. Okay. And what happens if rho is good? So let's say rho is almost equal to 1 here. So I'm going to say that my model approximates well my objective function, meaning that for the next step, I'm going to validate that step. And for the next step, I'm going to increase my step size parameters alpha because I trust my model, my local model, and hopefully I can make a bigger step next time. That's going to bring me faster to the local optimum. So if we include this strategy in there, okay, which is computing the model decrease and compare it to the actual objective decrease, what we're going to have is the algorithm R2, quadratic regularization algorithm, which is the one we're going to study in this talk. So here in this algorithm, we work just like gradient descent algorithm. We compute step, we compute the candidate, we compute the model reduction here, we compute or indicator rho k that tells us if the model is good or not. If the model is good, that is, if rho k is greater than eta 1, so we can also see in the right-hand side, we're gonna consider it a success, and we're gonna make a step. And we're gonna also update. So if rho k is lower than eta 1 parameter, okay, which is an entry of my algorithm, if rho k is lower than this eta 1, I'm gonna say, okay, so the step is not good. I don't want to make this step. Reject this. And also I'm gonna adapt my step size according to eta 1 and eta 2 parameter. That is, if rho k is lower than eta 1, what is that? I can do the step, I decrease the step size. This alpha here. I increase. You can see over there. And if rho k is greater than eta 2, I consider it very successful. That's very successful iteration, and I'm gonna increase the step size parameter. So basically, this is how it works. So depending on what rho k is, you decide to make a step or to increase or keep the same step size parameter. Okay. So now let's see this algorithm in light of the multi-precision context. So here are two examples where multi-precision can arise us. So first one is neural network training. So maybe you're familiar with that already. So the objective function in neural training can be viewed as that, like overly simplified or something like that. That is, n is my number of examples, like in training sets. And my objective function is the sum of fi function, which is the output of my neural network for every of these examples. Okay. So the NN basically are trained with gradient descent algorithm, the one we just seen. But since the gradient is too expensive to compute because The network might be very large, or you have too many examples. What you're going to do is that you're going to sample the gradient. That is, you're going to not consider all the examples of your training set. You just take a mini batch, see here, and you're going to approximate the gradients. So denote it with a hat here as just the sum of your training examples. So that's how you get an approximation of your gradients here. So this guy here is not the exact gradient, but it's way cheaper to compute than the exact gradient. And this here, all the multiplication precision can come into play depending on the size of your mini batch. You have precision, a lot of precision, expensive to compute, or less precision, but cheaper to compute. You can also have that for differential equations. So let's say your objective, what you're trying to optimize, depends on the solution of your differential equation, which you do not have an explicit solution. So first problem, you do not have gradients usually. So it's exactly the same framework as black box optimization. So what you can do is to try to approximate this gradient with finite difference, for example. And here just an approximation of the data. And also the solution of your PDE can be computed with typically numerical methods with difference. So basically, you do not have the exact solution. You just have an approximation of the solution. And you're going to have errors in the evaluation of your objective function because of that, because you don't solve it exactly. So what can we do? Here, phi or p in the next of the talk going to be the precision level. Right? So in the DNA training, if I want to increase the precision level, I'm going to take more examples to train my deep neural network. I'm going to increase the size of my mini batch here. The differential equation complex, what I would do is to solve my PDE over a finite grid, like a more or less coarse grid, to give me a better approximation. So here, that requires more computational power to compute, solve the equation with that fine grid, but it's very persistent than each one. And so basically, that's how you can switch precisions. And the whole thing is to know what precision you should use in your algorithm to evaluate both your objective and your gradients. Okay, so if we put that in a mathematical context, what we're going to have is at pass an approximation of my real objective function. And I'm going to suppose it's bounded in absolute value, but it's different between my real objective and the approximation of my objective is bounded by some omega. Omega that is given also by the first level that I acquired on the evaluation of my objective function. And same thing for the gradients. But here I'm going to bound the normal gradients, the normal difference of gradients, multiplied by the gradient. So here is an absolute error I'm going to require on the objective function. Here it's only a relative error I'm going to ask on the gradients. So just keep in mind, omega f is the error on the objective, and omega g, omega nabla here, so is the error on the gradient. So if we look back at the objective functions, f here in blue, what I'm gonna compute with my f hats is this red curve, which is my objective function with some noise. Okay, I cannot compute the blue function, I can only compute the red one. So here I compute it with a precision level like P1, let's say, and if I increase the precision level to P2, I'm gonna have a better approximation of my objective function, but that's gonna be more expensive to compute. Okay. So let's have a look back at our R2 algorithm. What we're going to have to change in our algorithm, gradient descent or fancy version of gradient descent algorithm, that's every time I compute the gradient for the functions, I'm going to replace it with the approximation. Okay, but if I want this algorithm to converge, I'm going to make sure that some conditions here are ensured. Okay. So what are these conditions? The first condition is that the error on the objective should be lower than some kappa f supplied by the whatever decrease. So if we look at what is the model decrease, here it's nabla f multiplied by the step itself being like step size parameters multiplied by the gradient here. So basically, this guy here is alpha multiplied by the normal gradient at 42. So it tells you that when the gradient gets really small, okay, next to this minimum, you're going to ask more and more precision for the evaluation of the objective function, okay, because there are very few variations there. But if you have big gradients, you can make each step, and if you have few variations here and there, it doesn't really matter because you still know you're going to have to decrease, okay, that's when they're almost close in big precision. This is what it says. Okay, let's look at the second condition. You need kappa to be lower than half of the one, which is the parameters of the size if you're successful in your iteration. So basically, what it says here is that if you want to tolerate more error on the evaluation of your objective function, you have to reject more steps because you won't be able to tell if you make an actual decrease in the objective function or not. So if you want big error on the objective function, you can reject more steps. The third condition, what it is, you just need to bounce error on the gradient by some constants. And the last condition here tells you that some of the error you have on the objective and the gradient should be lower than half of 1 minus 2, meaning that the more relative error you want to tolerate, the smaller you're going to have to be detected. Why is that so? Because if you tolerate more error on the objective, you're going to have to reject more steps. So the condition. But that's going to make your step size parameter to shrink and shrink and shrink and shrink more and more. So you counterbalance that if you don't want to be stuck before reaching the bottom minimum, you're going to have to decrease this guy to accept, consider more steps as very successful so that you can increase the step size parameter and counterbalance this effect by increasing the step size. But you're sure to reach a low double minimum. Looking at what it says. Okay, and you're gonna have at every step choose a precision, sorry, P, so that you ensure these conditions. So it's up to you to find this value, you need to find these precisions so that you ensure these conditions. So far nothing new. This is result that only 40 years old now. So far I haven't done really anything new, but in our context, it will be slightly different. So in our context, we're going to suppose that the errors come from not as receiving deep neural network training or the equations, something we can play. We're going to play with it differently. We're going to suppose that run or computations on machines like laptop or graphic cards or whatever, and we can switch precision level as like with how many bits do we compute the results, and that's going to be your precision levels. Okay, and that's interesting nowadays because with the increasing size of neural network, so basically neural network becomes more and more complicated to train, takes more time, more energy, and one way to cope with that is to perform the operation with less precision. So nowadays you can find some graphic code living in 16 bits, for example, instead of 30 bits. And so we're going to try to take advantage of that. And we're going to play with precision levels, like for example, 16 bits, 32 bits, 64 bits. If we do that, however, we're going to have to consider extra errors, which is what happens if I have a finite precision representation of my increment X and my step S. And basically, if there are low precision, I'm going to have to take extra errors that are usually not taken into account. In the previous version of the algorithm, I suppose that my candidate says is computed exactly. But now, if X and S are two floating point numbers, low precision, that is not true anymore. Like candidate and compute is not this, it's something different. And we're going to have to take these kinds of errors into account. Same thing with model reduction now. Model tree that I compute, that I can compute exactly anymore. I'm going to have errors. And what we're going to try to do is to take these errors into account in our gradient descent algorithms. So before seeing that, we have to dive into finite precision complications and how numbers are represented in machines. So probably familiar with bit representation of numbers in machines. Okay, so all the machines represents a number with a sequence of bits here. And okay, so here are some examples. Most of your modern processors and your laptops run in 64 bits. So the size of the number represented in machine 64, a GPU typically 32 bits. Maybe I'm wrong, so you can correct me with that. And the first modern, what we can consider modern computers, is the 3 both in 1941, run to the thing with 22 bits. Okay, so we're gonna try to understand how like numbers are represented in machine, but first let's see, for us human, we interpret numbers. Okay, so as humans, we count with 10 digits starting from 0 to 9. That is the base which we compute is 10. Now, if I look at this number, 4 million something, well, so to me it means something, but how do I, what does it bring me? It means that I can add, depending on the position of the digits in this sequence of digits, I'm going to add them with the base at powers position of digits minus 1. So these two here means it's 2 multiplied by 10 for 0, which is 1. Then I'm going to add that with the second digits. I'm going to multiply by 10 for 1, 10, and so forth, and so forth. And for the last digits, 4 million here. Okay. The interesting thing is that some of the first computers were actually built to run on base 10, not on base 2. But since then, we discovered like that it's way more efficient to do it in base 10 due to basically how we build the computer with silicium and stuff. But back then, they did not have all silicium logic gates and stuff. So they had complicated ways to count numbers, and they basically started to do it in base 10. Okay. So now let's get back to also bits and so machine count them. So every bit can take 2 possible values, 0 or 1. So machine counts with 2 digits. Okay, so we can count in base 2. And this is how we can interpret a sequence of bits in base 10. Finally here. Then I take my first digit, the 0, multiplied by the 10 by the base, add forward the position of the digit minus 1, and I'm gonna add them this way. So the last digit for 15. I add all these together and I get the same numbers I have 4 millions. Okay, so this is an integer represented in machine. What if I want negative integers? I'm gonna say 1 bit to give me the sign of the integer. So the last bit here, if it's 0, it means it's negative, and if it's 1, it means the number is positive. What now if I want to have real numbers? So this is fixed points, so first machine probably use fixed points, but we don't use anymore. Let's see why. You decide basically where you want to put your points, and everything on the left-hand side of the point will have positive power of 2, and everything on the right-hand side will be a fraction part, basically on that. And this is how you get a real number. Problem with fixed points is where you put the points actually, and you're gonna have to balance precision or range. If I put my point here, I don't have much range. Typically, I will be able to count only to 8 or something. I can represent a number greater than 8 here, but I have lots of precision here. I can represent very small numbers. If I put my points here, I'm gonna have big range, but low precision. Like my fraction part, is completely small. So that's how we came up with floating point numbers. So floating point numbers are 3 parts: the sign, as we've already seen, the exponents, and the significant or mantissa or fraction. So how is how we represent floating point, which is basically what you have all on your laptops nowadays. So the exponent is an integer. And the significant, you have to imagine you have a point here and all ends with fraction point. Okay? So this fraction point here. We're gonna add all the mantissa that is here. That's basically a fraction part of my number. And how do I compute a floating point? I say it's sine multiplied by 2 at powers exponent minus bias, so that these guys can be positive or negative here, e minus p, multiplied by 1 plus the fraction for t star. Okay, and this is how we can represent big numbers with exponents big or small numbers with exponents small here with good precision. And if we look at how floating point numbers are dispatched over the real axis, okay, obviously you can have negative numbers from them. So you can have lots of numbers around 0, and as the numbers goes bigger and bigger, you can have less and less numbers. The degree tells you that the precision of the floating point numbers is relative to the magnitude of the number. Okay. And there is an interesting thing we have here is a Nash epsilon. So Nash epsilon is the smallest fraction which is ultimate p stack here, and basically it tells you what is the distance between one number and the next one you can represent. So if you have the floating point number 8, the next one you can represent is 6 divided by 1 plus the percentage. Okay. And now we come to IEEE 754 norm. So as floating point numbers become more and more popular on computers, the norm was implemented to tell you how rounding errors should happen. So what is rounding error? You have two floating point numbers, it's y, but when you add them, you do not necessarily end up with a floating point number, and end up in between both. So you're gonna have to round these guys here somewhere to a floating point number. Okay. And this form tells you that to perform an operation with one of the standard operator, that is extraction multiplication division, your error, so here, so which is delta x squared in the operating once, y should be lower than your machine precision, epsilon machine. So basically it tells you that your exact number is going to be rounded down or up to one of the closest floating point number. Okay. And what is implemented in most of the machine is rounded to zeros that we do always have. But the IEEE norm just tells you can use this one on that. Okay, now let's get back to optimization problems. I consider malicious function it's just some addition, one addition or subtraction. So what I'm gonna have is what I can compute is this one. Okay, so this one is gonna be my approximation. Okay, and when I put an FL here, it means for computations. Okay. So if I develop that, so we can put it here. If I develop it in the end, so this is my exact objective function, but what I'm going to compute with my precision arithmetic is this guy here, which is multiplied by some rounding error. Okay, so I cannot have that. And depending on the number of bits on which you represent your numbers, this delta, your epsilon machine, going to be bigger or smaller, and that's how we're going to switch positions. All right, so let's now look at some examples of what can happen if you don't take rounding errors into account. Yeah.
I just have a question about your machine epsilon. When you talk about it, is it always the same one or not? Because in practice, depending on where you are on the grid, if you represent your space on the grid, the space between two numbers is not the machine epsilon between two numbers, not the same.
Yeah.
So in your previous slide, you said you take the machine epsilon at the same number between two real numbers, but in practice, depending on where you are on the grid, machine epsilon is different. If you are 1 or 2 exponent 50, the next number is different.
The machine epsilon is always the same. Right?
No.
No?
No. If you define the next number after 1 minus 1. It always fits on that.
So you define your epsilon machine and 1.
It's
not
the worst distance possible on the.
in the worst, but if you are 2.50, the next
No, it's a
number
really,
is
right?
okay.
So the larger you go, the smaller it gets. Because your ingredient is bigger.
Okay.
Are you referring to that figure maybe?
Yeah. Depending on where you are on the grid along the line, the machine epsilon is different because the number I represent, if you are 2 exponent 50, the next number is 2 exponent 50 plus 8, for example. Whereas in 1, the next number is 1 plus 10 exponent minus 50, minus 16.
Yeah. This
So
is what you
machine
have
epsilon is
between
different.
1, 2, no, because you multiply it by 6. So if x is big, the next number will be further away.
Yeah. But when you talk about the machine epsilon, do you take as a function that depends on x, or you take?
No, machine epsilon is just 2 at power minus
Okay.
the number of bits in your machine, so it's always the same.
Okay.
Dominique wrote on his slide, machine epsilon is a relative quantity. So it's a fixed number.
Oh, sorry, yeah. No,
Not-
machine epsilon is, yeah. Fixed
It does not depend on any x. It's just a property of the floating point system, but it's a relative measure.
Yeah, yeah, sorry, that was confusing, yeah. Okay. Okay. Oh, and so how many times I have? Okay, let's move it back. So first, well, 4. Okay, so basically, Iraq absolutely decided to index the weight. USA goes to war to save the weight. And what happened is that the Iraq decided to send a good missile to a US military base in Saudi Arabia around here. So in theory, the US Patriot defense system should have intercepted the Scud missile sent by the Iraqi, but it did not. And this is what happened. Basically, what happened is just calculation of rounding errors. So this is how Patriot system computed the time. It's all about how to compute the time. So this system had a 10 Hertz internal clock, and that is every tick of the clock, it would compute the time as time is equal plus time equal time plus 1/10. The problem here is 1/10 you can actually do that in the machine. Okay, because it becomes in base 2. And in base 2, you can express 1/10 as the sum of 2 at power minus something. So what happened is that in the 24-bit register, every 10 seconds, they would add an error of approximately like small error here. Okay. But when you run it after 100 hours, what you get is computed time, but you have 0.34 seconds of error. That is, the clock of the Patriot system was 0.3 seconds late. Oh yeah, so that's not big, but when you try to intercept a Scud missile flying at 1.6 kilometers a second, you missed it by about 500 meters. So basically, the Patriot missile that was sent to intercept the Scud completely failed, and the Scud missile hits a meter guidance. So that's an example of how you should take rounding errors into account. So here it's a bit special because what you do is that every time you add 1/10, and this is always the same rounding errors you add again and again and again. When you have complicated equations, or when you try for the computed dot product, what happens sometimes is that the rounding errors from one compensate the other, and in the end you're not too bad. But here, every 10 seconds, you add exactly the same rounding errors, and that accumulates. Okay, so that's an example of what can happen if you don't take rounding errors into account. The second example is here to highlight an overflow effect. So basically, an overflow occurs when you try to cast one number into another number with a different representation. Okay? So this is the Orion-type space launcher, which computed the horizontal velocity as a 464. But in the guidance system, what they did is that they cast this 464 into an integer space, 16 for some reason, I don't know which one. But anyway, what happened is that the short number was so big that it could not fit as an integer 16. That is, it was greater than the maximum possible range of what it can represent. And what happened is an overflow. That is, when you register into integer 16, it just tells you, I have infinity. So everything you compute after that is just infinity plus something is infinity, infinity multiplied by something is infinity, and you can compute anything. So what happens is that the guidance system failed, and that the space launcher was slide after falling spin on slides. It's pretty sad because this one was the first slide of that space launcher. So, oh yeah, and we're gonna have to keep that in mind because what we're gonna do is that we're gonna switch between precision, float 64, float 16. So this overflow might happen, and we have to keep that in mind. Okay, so these are pretty dramatic examples. Like I do not pretend to be that dramatic with my algorithm. Thank you. And these are the three floating point formats we're gonna play with. We're gonna play with in the rest of the talk float 16, float 2, float 4, which are floating points represented on 16, 32, and a bit. So here you have the like greatest, smallest number, and Nash Epsilon 43 floating point formats. And the idea is that if you perform computation in 16-bit, 32, 64 bits, if you switch between precision, you basically multiply the computation time by 2 and the energy by 4. Okay, so the energy consumption is basically based on the area of the chip, which is multiplied by 2. If you increase by 2 the number of the 4, sorry, if you increase by 2 the number of 2. So that's a rule of thumb. Yeah.
Question, how is that? Is it the cost of switching, or if you switch, 32 will come from 4 times?
Oh no, it's the cost of doing one operation with this one. So one operation costs twice as much time and costs as much energy.
If you do that,
Yeah. So that's cheap, but you don't have great precision machine. It's pretty big. That's costs you a lot, but you're very small machines. Meaning that your rounding error is going to be smaller.
So the switching is 0.
Yeah, we'll consider the switching is 0. If you want to switch from one another, what you're going to have to do is to basically just switch the formats of what you want to use. Okay, so now let's get back to our algorithm in the context of finite precision computations. So after what I presented, if you look back at our algorithm, we're going to say, okay, so basically every time I compute something, you're going to have rounding error occurring, and whatever is in red here is some errors to be taken into account. So it looks here pretty bad. But we're going to reduce the range of what we're going to consider to only small, like reduce the range. We're going to only compute that step is computed exactly, the candidate is computed exactly, and model reduction too. So we're going to denote the ampersand hat here to point the fact that we're not computed exactly, and FL here to say it's a floating point computation. We're going to suppose that row or indicator is computed exactly, but in practice you can still do that, okay, because this requires just one subtraction and one division, so you just have 2 operations. And on your machine you can simulate very high precision format. For example, on your machine, you can simulate float 260, which has massive precision. So you can compute this on fairly actual, and it's cheap to compute. Okay, so let's look at our candidate computation. So here, my inexact gradients are going to be called G, okay, which is here. So here is in my incumbent is in dimension 2. Okay, so this is the gradient I compute, and I want my candidate ideally would be that guy here. But when I compute the step with floating point arithmetic, what I'm gonna have is that I'm gonna, so that basically is the element-wise multiplication of alpha with the elements of my gradients. Okay, so what I have is not alpha G is something like that, where rounding errors occur everywhere. So what I have is not the gradient, so the guy I can compute here with my steps, so the step is somewhere here, okay? And here, it's not yet done because we compute a candidate from the now inexact step. When I perform the computation for the candidates, I'm gonna add I can think them plus my exact step, and that was precision arithmetic. So I'm gonna have one more rounding error, and C hat, the candidate I compute, is not what I wanted here initially, but that here. Okay. Because rounding errors. And this is, so this error is not too bad, as relative error, not too bad, but here can get pretty bad, especially when you step is small compared with the incumbent. Well, because if we look at this equation, if x is big, delta x, even if delta is small, it's not really small, it was simple for 16, for example, these guys can actually be bigger than your step. Meaning that what it computes, you have no idea of what you're computing, because the numerical noise, it's so big that the step is not, you don't even know where it is. Okay? So here I put my candidate here, okay, it can be anywhere around here because I have no idea what this only error is. Okay? So that we're going to take into account, and how do we take it into account? Basically, we're going to define an indicator P here, which is the norm of x divided by the norm of s. Tells you how big is x compared to step s. So if P is big, you should sort of pay attention. Okay, so that's for the candidate computation, and now let's look at that model decrease error. So this is don't give too many details, but this is material and how rounding error accumulates for dot product. Basically, what we're doing here is dot product. Okay, so if I accumulate all my rounding error, what we do is we model this way, okay, which is so the inexact model reduction I compute is my exact model reduction multiplied by 1 plus theta n being bounded by m, so the dimension of my vector multiplied by the epsilon machine being related to what format I'm using to perform these operations here. Okay. Once we have that, we can perform an analysis that I'm gonna spare you. And we have convergence condition for our algorithm to a minimum, a local minimum. Okay, so these are the old conversions I had when I only considered an exact objective and gradient regularization. And this is now my new conditions. Okay, when I consider inexact candidate computation and inexact model decrease computations. So if we look at them, they look pretty similar. So that's here is good news that say I can just replace this condition with my inexact model decrease. So it's pretty straightforward. So this is the same except this guy is okay. And this is where the convergence analysis comes into play because new k is this big slush here. Okay. Not very pretty, but let's look at what we have in here. So what we're in here, this term is gradient toleration error. Okay. I have the errors, this gamma n is related to model decrease error here, and I find over there. And my phi here is related to how big is my candidate compared to myself. Okay. So I'll need the more details, but basically this relationship tells you how the errors, gradient errors, model, and candidate interplay with each other. Okay. So then the results of the analysis give you more detail about that. We implement our algorithm with these new conditions. So we're gonna consider a bank of 116 problems that you can find at the smooth optimizer. Yeah, okay. So Tanguy can tell you more about that here, probably. Okay, so a stopping condition for algorithm, we're going to say if the norm of the gradient is smaller than 10 to the power minus 6, or if we reach a maximum number of iterations, 10,000. We're going to use 3 precision levels, 16, 32, 64. And we're going to, for the sake of this experiment, we can compute exactly the error bound with interval arithmetic. So I won't give you any detail about that here, but we have tools to compute these omega and omega lambdas. Okay. So what are the results? The result is that we can solve, that is, reach a local minimum with this condition. Gradient of that. Other than 10 to the power minus 6, we're 65% of the problem. Okay. For 20% of the problem, we reach the maximum number of iterations that were allowed. So that tells you that, remember, it's a first order method, like a gradient descent, not very efficient compared to second order method that you've probably seen. And we have a precision fail for 15% of the problem, meaning that float 64 is not enough to have sufficiently small errors to guarantee that I can converge. At some point, one of my conditions here, so the that one or this one or that one, is not respected anymore. Even if I use the maximum precision possible, so PS here is the maximum, like here at the maximum, one of these two conditions fails. So I'm just gonna stop the algorithm. Okay. Now look at what are the evaluation details form. Okay, so algorithms switch dynamically with precision between float 16 and float 64. Okay, with some strategies implemented. I won't give it here. And this is the objective evaluation. So the objective is evaluated about 0.5% of the time with float 16, about 60% of the time I'm going to use float 2, and 40% of the time I'm going to use float 64 to evaluate my gradients. Okay, so that tells you I don't always have to evaluate my objective with maximum precision. I can switch between, and that saves me time and energy. Okay. For the gradient, what we can see is that we can't really use float 16, okay, but we can use float 32 a lot, and we need to do that float 64. Okay, so why is it different between the objective and the gradient? So that remember, the objective and the gradient is relative. Okay, and the precision we need on the objective is absolute. That is, when the gradient is very small, I need lots of precision on the objective. So that's why we have this difference between objective and gradient relation. Okay, so I implemented my algorithm. I tried that. Yeah, it's well, okay. It doesn't look good. So probably that there are 15% failure of the algorithm. That is, I don't have enough precision with float 64. And float 64, I don't have like more than that for the machine, except if I want to simulate it, we can take lots of time, and I don't want to do that. Possibly 35%, because for 20% of the problem, we reach maximum number of iterations. So maybe for this 20% of the problem, I don't even have enough precision. Maybe. Another limitation I did not talk about is the model within our model. We want theta n here to be lower than n times epsilon machine. Float 16, epsilon n is 10.3. That is, that limits implicitly the dimension of my problem to be less than 1,000. Okay? Because if this guy is greater than 1, the liquidity error is more than 100%, and that's useless. Okay? With float 32, that limits the dimension of my problem to 10 million. Now let's put that in perspective with different network training. Basically, if you look at AlexNet network for image classification, it has something like, I think, 60 million parameters or so, and it's trained perfectly well on float 32. So according to my analysis, like, it shouldn't be greater than 10 million. Okay, and since I'm head by Huawei contract, I cannot really tell Huawei, you cannot really train your neural network with float 32 because it doesn't work. But if you want to train it in float 16, basically try to have a neural network with only 1,000 parameters. So that won't do. Okay, so let's take a step back on what we have here. Our algorithm, I'm here to guarantees all the time convergence, but it's based on pessimistic bound. Okay. What we have is bounds, omega f and omega lambda, that are always guaranteed. When you do that, you always suppose that the worst possible case of rounding errors accumulation happen, which is not true all the time, or you're very unlucky. Same thing for model prediction. We have a guaranteed bound, but it's pessimistic because I have to choose my precision levels according to this deterministic but pessimistic bound. Okay, and also in the convergence analysis, we have to play with the equation, and also there we add a bit of pessimism. Okay, so M-party algorithm, the one we have, is bulletproof, is warranted to converge if you have precision. Okay, but it's really probably not effective. So probably what we should do is not implement the conditions on the R. Okay, and we can see, we'll see in the conclusion what we can do about that. More insights. And still we have some hope, okay, with our analysis. So first of all, despite these very pessimistic conditions, what we see is that we can evaluate the gradient and the objective with 32 bits and sometimes 16 bits. Meaning that despite all the pessimism I have, with the conditions and the bounds, I can still do lots of things with half precision and 50-60 precision. Meaning that if I'm not that pessimistic, there are good chances I can use even lower precision levels than that. Okay, so if I don't want to implement my pessimistic conditions, but are too restrictive in my algorithm, what do I do with that? So this is not yet referring to garbage. Okay, okay here. But once again, what it tells me is how the error interplay with each other. Okay, it tells me how the gradient relation error can interplay with the model, decrease computation error with the ratio of step with my current incumbent. Okay, so that is a nice analysis that tells you how these errors interact with each other. And if you have some insight on what are the errors when you're running your algorithm, you can say, I'm going to put more precision on that computation of model with this. Or I'm going to try to have more precision, like decrease my gradient error or something like that. Okay. Our conclusion. We have developed an algorithm on CUR2 that takes all the rounding errors into account that can involve in your algorithm. Okay, that is not only objective and gradient evaluation, but also all the intermediate computations within the algorithm. So for the convergence analysis, that tells us this big U. Okay, that tells us how errors interact with each other. And we've seen that despite all the physics, we can still use other formats in 64, so we can still save time and energy between that. And what can we do about this pessimism I was talking about? What we can do is to say, instead of having these four conditions here, what we can do is that I just need some probability that my condition is respected. Okay. So here we won't have guaranteed deterministic proof convergence that we have with CUR2 is that we're going to have a guarantee of convergence in terms of a probability. You're going to say, I have this probability to converge to a local minimum. That's what we're going to have. And this, you can have it also the condition of the gradient. Okay, so we're going to say the condition of the error by gradient can also be probabilistic. And after it's all about how you tune this probability, like level of probability, to guarantee a certain convergence, like it's probability. That's one way to relate that. And after, what we can do, so mostly in the test context, like deep neural network, the requirement you usually okay, I'm using something here. What you usually say when you take a mini batch, okay, you don't want to have an error on the objective of the gradient, like a deterministic error. What you just need to have is the expectancy. So the expectancy, sorry about that. You just need the expectancy of your gradient, okay? So basically that's the error between the actual gradients and what you compute, okay? And the expectancy of that with your random variable, okay, which is basically what you choose in the batch, should be greater than some u by norm of gradient. Okay. So basically, you want the two, the expectancy of the difference of the two to be not big. And this, if you take the expectancy, is way less training than fitting the deterministic error. Okay, just need the expectancy. We got to do that. And the idea is to be able to use unfair and two for digital method training is to put all that together, not considering deterministic error, but considering probabilistic error. So probabilistic error, we're gonna need them for computation error, so finite precisions, arithmetic, and we're gonna have to put the expectancy kind of error due to the events when you select or you sample for the gradients. Okay, and hopefully, if we put that all together, we're gonna have to use unfair version that we can actually use for the economic gradient. So yeah, that's the goal. So thank you for your attention, and if you have any questions.